Hi everyone, welcome to this second lecture of the class Dynamical Systems, Networks and Applications. So today we are dealing with the qualitative analysis of some nonlinear PDEs, which come from a neuroscience context. So in fact, today we will deal with reaction diffusion system. So this is the outline of the lecture. In fact, we are discussing mainly three equations, three reaction diffusion systems. So the first one will take place in a one-dimensional domain with respect to the variable x. And then we will generalize somehow to two dimensions. Then we will make some parameters depend on x. And finally, we will connect with the stuff that we discussed at the previous lecture, in the lecture one. So, any questions? I think for now, there's no question. So, this is the first equation. So, it's kind of a toy model for more realistic equation. So what do we have here? So as I said before, we are working with a dimension 1 in space. So we are working on the domain 0, 1 with Neumann boundary conditions. So here it means what? It means that the derivative of u and v at 0 and 1 are equal to 0. And as I said, this is a nonlinear equation because here you have a cubic term. Right. So let's do some remarks because in fact some classical techniques do not work for this equation. Why? So there are classical remarkable works from Marion, Robinson, and Teman, for example. But these works, in general, have this term in the second equation. So here, if you add a minus delta V for delta positive, it changes the technique. And also, as we will see that 0 belongs to the closure of the eigenvalues of the linearized operator. And so this brings some technical difficulty. So just a comment, so we can prove that this solution has, so this equation, sorry, has a solution, and we work in the space L2 times L2. So we work in U belongs to L2 and V belongs to L2. So this means that if you choose an initial condition in L2, U in L2 and V in L2, then you will have a solution for this equation, which is defined for all positive time. So I'm not going to discuss so much on that. And I'm moving forward. And we're now claiming the first result, which is if you choose this coefficient alpha to be negative, then whatever the initial conditions you choose in H, the solution is going to 0 in this Banach space in H. Is everything clear?
Yes.
Okay, thank you. So I'm going to give some details about this proof. But here are the main ideas. So if you take this derivative formally, you can prove this is negative. Okay, but for the details to prove rigorously things, I choose to work on Galerkin approximation. So I will give details right now, but we work on Galerkin approximations. In that way, everything is regular. We can take the derivative that we want. And then we gain compacity and apply the Lassalle's invariance principle, which I will detail after, and then we can conclude. So I'm going to give some details. So I'm going to work in the blackboard, but I let you a few minutes to prove the first point. So I let you think about that by yourself, so 5 minutes, and then I will give the details. So just take this quantity and do the derivative with respect to t, and just do it formally, like you can do if like everything is very regular, and you will show that, you prove that this is negative. So I let you 5 minutes. So, all right. So one of the students gave the good answer during the exercise. So yeah, so I can do it quickly. So what he said, I'm just writing what the student said. So we are considering this quantity. So if we take the derivative of that, let's call it v of t. Or v, just v. This is equal to 2 integrals But then if you replace by the value of ut and vt from the equation, you get you can hear me, right? You hear me well, right?
Yes.
Okay, great. And so as Mr. Cassis said, so I forgot the alpha u here. You have the alpha u, which is negative. And so you get 2 times the minus integral plus, and using an integration by part, you will get that. And since to the boundary condition, thanks to the boundary condition, we got that. So, and as you see, this is negative. Okay, so this is the key point of the proof, this simple computation. But, so this is a small exercise. So, but now I'm giving you some theory. So, to write the details of the proof rigorously, we will need to use a version of the Lasso's principle. And to start with, I'm going to introduce what is called the omega limit set. So what is the omega limit set of x? So here, let us assume that X is a Banach space. And we assume that we have a dynamical system on X, which means that we have a function phi, capital Phi, from R plus times X which takes values in X and at each t X it associates a value in X which is phi of t of X. So, and so phi is continuous there, and phi 0 of X equals X, and also phi of t plus s of X equals phi of t of phi of s of X. So this is generally called a dynamical system. So the solution of our equation 1 So here x is the initial condition, and this phi, so so when I define that, then phi t of x for t in r plus is the trajectory associated with my equation and with an initial condition x. So this is the trajectory. So associated with the equation, with the dynamical system, which starts at x. All right. So I repeat, for a given equation, so for example, for equation 1, my phi here corresponds, is the tool that gives the trajectory. All right. So once I have, yes.
Monsieur, j'ai pas fini de noter là.
Okay, I will come back later. Don't worry for that, okay?
Okay.
Okay, now, so now I can define which is called the omega set of x. And this is the important stuff. All right, so it is defined as the intersection for all t, for all positive t, of the union for s greater than t of phi s of x. And I take the closure of that. So if you remember your topology class, this will be a closed set as an intersection of closed set. And so what is that object here? What is the omega limit? It is the region that my trajectory which is ensured from x and associated with an equation, an evolution equation. Here we're dealing with our equation 1, the solution of equation 1. But I just take what is going to happen for large t. So here, region that my trajectory visits asymptotically. And when I say visit, because I have the closure, so that's my closure visit. All right, so Yeah, this is very important because when you consider dynamical system, this is what you see for large T. Every other things disappear. Okay, and now, yes.
Monsieur, excusez-moi, en fait, je ne comprends pas très bien. Phi, c'est une application?
Yes. So phi here.
Ici, ce n'est pas une application. Ici, c'est des ensembles.
No, it's an application. So my phi, you give two things: a positive number, which is a positive number, which is the time. Okay, here this is the time.
D'accord.
This is a general definition, but in application, the definition of that is related here. This is the time, and here it's an initial condition. So when you define for example, in equation 1, the first theorem, the first result was the existence of a solution. So if you here x, for example, in the application in the equation 1, x is a given u and a given v in L2, a given u in L2 and a given v in L2, and then you have a solution which is defined for all t, and so my phi s of x, so x is my initial condition, is the solution at time s that started at x at time 0. I think it's clear now. So if you remember, for example, I remember that you studied the Lorentz system last year, and then you get this chaotic attractor. So this thing is are the points that your trajectory will visit again and again. And I take the closure because, yeah, it's not only the points that I visit, but the points that I will pass close, as close as I want to. Okay. So this is a classical idea. So if you never heard about that, it's just the first insight, and you can do research. You will find a lot of examples of that. Okay, so now I need to come back to my proof. So I'm going to erase things. And so omega of x is the omega limit set of x. All right. So don't worry if you didn't write that, you can find this definition. It's very classical things. What is less classical? It's what I'm going to say. It's the Lasso invariance principle. It is very classical, but I will give a version that is well adapted to our problem. So now I'm giving a theorem. So now let's consider, for example, a function v. So we assume that v So V is an everything is continuous, but V is an application from X into R, but it's positive. Is a continuous application. Such that for every X in X, V of phi t of X is a decreasing, is non-increasing, So, for example, we can take V. We can take V as the norm for example, in the example that we discussed at the beginning, for the equation, you can take V of UV equals since you computed this quantity, it's negative, and then you fall in this case. But there are some things that I didn't talk about. You have to be allowed to take the derivative over t. But okay, but this is a good candidate for our equation. So you can think V is typically this kind of quantity. Typically, it's from a physical point of view, it's an energy. And if your system loses energy, it's a good candidate. So, and then, those are my assumptions. And then, then what? For every X in X, for every Y in the omega limit set of X, and for every T positive, so of course, we assume that my solution and my phi is, but I have assumed that it's defined for all t. So you have that phi of t of y. So sorry, v of phi t y equals v of phi 0 of y, which is actually v of y. So I hope you can see that this is important. So this is important. You can see? Yes. You see that?
Yes.
Oui, c'est bon.
Okay, great. So what does it mean? It means what? It means that V, this quantity, remains constant along the trajectory. So this means what? This means when I have this kind of things, you look at what's going on for large T, and then if you start with a point which belongs to an omega limit set, my function will remain constant. And as we will see, this will be the key point, one of the key points to prove rigorously our theorem. So as I said, what does it mean? It means that V remains constant on the omega limit set. All right, so now these are general things. You can look at it, and it's a good exercise to look at these things. We will find some different kind of versions of this. This is the Lasso's principle. There is various different versions. Lasso's principle. All right, so we have some time, it's okay. Okay, now I'm going back to my equation. So, as I said in the main ideas of the proof, we will work with Galerkin approximation. So, let's write here the equation, right? So the equation is the following one.
U.
Okay. So a classical way to even prove the existence, because you start with solutions that are in L2, you have no clue. So of course, I'm not talking about that a little bit. So if you are in L2, you have to take this. You have to take this derivative in the sense of the distributions, and so after you have some regulatory results. But from our perspective, is it worth to work with approximation? So just I'm just recalling how do you construct the solutions of that? You look for functions un, and the same for vn, which writes as a sum of. So of course I don't write everything, because but it's depending of course on t and x, and so I work here with coefficients which will depend on t, and here functions which depend on x, and so this phi k of x are the eigenfunctions of uxx, and here you know that you can write phi k of x equals square root of 2 if k is greater than 0 and equals 1 if k equals 0. And the same for v. So you look for solutions which write t and phi k of x. So you can see that these functions here are very regular. Okay, this is very regular. It's a cosine, and as we will see, this will be so. And I want that these solutions of what? So what are un and vn? I want that un and vn satisfy this equation. So u n k t. So this is a function only of t, and I wanted them to be solutions of the following ODE equals. So I will call this term I will call all this f of u. So this will be f of u. And so, or no, sorry, just well, it's the same, but I want to isolate the nonlinearity here. So my f of u here, I just consider it to be the cubic. So this will be what? This will be f of un, and the rest is the same, plus and here so you can obtain this equation by replacing u here by un, and then you take the integral, you multiply by a function phi k and take the integral, and you will get this equation. But the only thing that was not correct here is not, this term is not correct. So this, everything is correct, but this term is missing something here. So as I say, I need to take the integral and multiply here by phi of k. So let's do it complete, and the rest was correct. So plus alpha k. So now I forgot, I will not write the n here, maybe, or maybe not. And so what is the lambda k? You know? So we did that on the first semester. What is lambda k? Lambda k is all right. So as I said, if you
Monsieur, f de un, de un ou f de uk, unk,
No, UN.
UN.
UN is that. UN is all that. So F of UN. There's no K here.
Okay. Okay, but not the phi. Pour le phi, c'est pas à l'intérieur de la fonction aussi?
No. So F of UN here, my F, as I said, is just minus UN to the third. Okay. F with, as I said, F of whatever you call it, F of U equals minus UQ.
Oui, oui, I see, oui.
All right. So this is a function of X and T, but I multiply it by an eigen function and I take the integral.
Yeah, I understand.
All right, good. Okay, now you can see that if you want, you can sum up now, you can multiply again by a 5K and take the sum. And what do you, so let's do this exercise. You multiply this equation by phi of K and take the sum.
Yeah.
What do you find? I repeat, you multiply each side of the equation by 5K. So 5K depends on space. And you take the sum between zero. You sum up all the equations between 0 and n. What do you find?
We don't see, monsieur.
Yeah, I know.
We don't see.
I know. Yeah, I know. I wanted you to work on the exercise before giving you the solution. So just a comment. So this equation is an ODE. So everything is very regular. So yeah, this is only a cubic. So you can write it the details and you will find that this is an ODE. Everything is regular. So your solution is C. You can derive it is as regular as you want. The solution of that is an ODE, right? Because these are numbers, this is cubic. So here there's a sum, but there's a cubic. You can compute everything and you got an ODE. So this admits unique solution. A priori, you don't know if it's defined for all time, but you know that it exists for a given time. And so the point is that it is very regular. Now, if you sum up, so you multiply each of these equations by phi k and you sum up all the equations, you will find this equation. So it's the original equation, but here, so this is the projection of f of un in the subspace generated by the n first eigenfunction. So this is a classical thinking Hilbert spaces. This is defined by integral to 0 of 1 of f un phi k, and let's write the phi k, right? So this is a function which depends on x. So to make it maybe clearer, I will write here the dependence on x. So phi k depends on x, and here and of course you have dy. Oh, it's dy, sorry. Equations in French. All right. So now, again, now if you look at as you did before, you look now at this quantity. Now I don't have problem to take this derivative. Everything is very regular. And you look at that. You will find that this is negative. You need, however, to solve to be you need to show that the integral between 0 and 1 of p and f of un, or let's say dx, this is the same thing that you can take out the pn here. It's an exercise to prove that. I can do that. So when you have that, this is just the same computation that you, Mr. Cassette, did at the beginning, and I wrote quickly at in the blackboard at the beginning. So you just need to prove that. So this is true, but I'm starting here. So let's write this. So by definition, my Pn is the sum between 0 and n of the integral between 0 and 1 of f un of y phi k. So let me just write the dy here and here. So yeah, so now this phi k depends on x, and here I have un of x dx. But this is just a number, so I can take this out of the integral, and I find that this is the sum between k equals 0 and n. I will just make the separation between the y and the x, and I get the integral between 0 and 1 of f of un ck dy and the integral between 0 and 1 of phi k x un x dx. But now, again, I can put this integral here. I put this integral here, and with my phi k here, and this is the result. This is the result. So let's just write it. So no, sorry. Now I take the integral here, and I put the sum after. So basically I put the dy now at the end, and I do that. So I want to make it clear, it's a y here, and then integral 0 and 1 of un of x pk. So this is nothing but un k here. So all this stuff, all these things is just un. Here it's un of y. This is just because my functions phi, are not orthogonal basis. So this is just un k, and so this is my un, and so I got the result. So now let's move it quickly now. So we proved that, right? This is now proven, and then you have that. Now, so I want to apply the Lassalle's invariance principle. I want to apply the Lassalle's invariance principle. However, it is possible that for an initial condition, my omega limit set might be empty. In the theorem didn't talk about the existence. It didn't say nothing about the existence if the omega limit set might be empty. And if we want to prove that it's not empty, it is sufficient to prove that the trajectory remains in the compact set. So I need to prove compacity. There's some details, but that's the point here. I need to prove compacity. And to do that, I can just look at here the derivative of this quantity. So here it's the derivative of un with regard to the space variable. Okay, and everything works good, and you can prove that this is negative. So it's pretty much the same thing. You can do this exercise. I will not correct that, but it's an exercise. You can do it. You can prove that the integral between 0 of 1, this works with the derivative also. So here I want to take the derivative with regard to x and here also. This is, I can do the same. You can just take out here. Okay, and so you do the computation, and again, this is the proof it. This is like the same you did for UN and VN. All right. So what's interesting then? It's what do you have? You have that UN x this quantity. Let's call it. I call that. Let's call it. What do you want? Let's call it L. Right now, you have that L of t is less than L of 0. So this is bounded. And you have the compact injection from H1 into L2. So this means what? With the two inequalities, this means that my trajectories are compact in H. And since you have this compacity, this means that the omega limit set of any initial condition is not empty.
Monsieur,
Yes.
Sofiane dit de l'accepter, s'il vous plaît. Il a fini son rendez-vous, de l'accepter.
Okay. All right, so okay. Okay, so now the rest of the proof is the following. You can prove that the only point, because of the specificity of the system, I'm not going to give you all the details, but because of the specificity of the system, for each initial condition, the only point which can belong to the omega limit set is 0, 0. So just to finish, you can prove that for every U0 D0, you have that the omega limit set of U0 D0 is 0, 0. And then thanks to the compacity, this means that all the initial conditions will converge from that. We conclude that limit. Okay, it's just UN here. So in H, but then in fact, when n goes to infinity, this is going to converge to the solution of my initial problem. Everything goes well. So, okay. Let's go back to the presentation. All right, so yes, if you want to give all the details, there's some techniques to apply. But yeah, so you need to have this. So this is a key point. Then we work on Galerkin approximation, which allows to take all the derivatives that we want, and you can actually now take the norm in H1, and it might be that the solution does not belong to H1, but you take this Galerkin approximation and it belongs to H1. You have compacity, and then you prove that the only solution possible is 0, 0. So all the Galerkin approximations converge to 0, 0 as t goes to infinity, and you do have a uniform control between the Galerkin approximation and the solution in H, which gives the result. Hope you're not too tired. Okay, but this is only for alpha less than 0. If you did the computation, alpha negative is a key point for the proof. When you did your computation, you find minus alpha u squared, and this, or plus alpha u squared, but it works since alpha is negative. But then, so let's forget the x variable and just consider the ODE. So let's drop off the uxx. You have the following theorem. So you can solve the unit stationary point is 0, 0. If alpha is negative or non-positive, you can prove that all the solutions go to 0, 0. Actually, we did it even in the we did it for the PDE. So this is of course true for the ODE. Now, when you take alpha positive, a limit cycle appears. It appears through supercritical Hopf bifurcation. All right. And we have more than that. You have that all the initial conditions will converge to this limit cycle. If you don't start at the point 0, 0. So if you don't start at the point 0, 0, all the solution goes toward the limit cycle. So I guess I have a picture here. Yes. So I just draw yesterday this picture, which is, so you take, for example, an initial condition here. Yeah, so the x axis is not right here, but it's like you start at 0, -2, and your trajectory. So this is a trajectory. This is your initial condition, and then you follow the trajectory. You go there, from there you go there, and you have a limit cycle. All right, this is a limit cycle. So your solution started here, and then asymptotically you go around the limit cycle. So here, for example, the omega limit set intuited from 0, 0. So it's not a PDE, it's an ODE, but this definition also works for the ODE, will be this set of R2. Yeah. And you can start wherever you want, you will end up around this limit cycle. All right. Okay, I can give you a proof of that. Just make some comments. Oh no, my mistake. So, oh, okay. So I was hiding the x-axis with some features that I didn't see the x-axis. No, forget that. All right, so your general proof actually follows from the fact that the system is of a linear type. So I cannot give you all the details because it will take more than 2 hours, much more. So there is this book of Perko on dynamical systems, ODEs, and you have the proof. So it's interesting to go to the details, and you can also prove the occurrence of the supercritical of bifurcation. I'm just going to give you the proof, the idea of the proof. Two things. So this system, it's a nice example to introduce the supercritical of bifurcation because you can do the computation quite easily. So again, you can look at the book of Perko, and if you want to prove rigorously the of bifurcation, in particular, if you want to prove that the bifurcation is supercritical, which means that you have a limit cycle which is stable that appears, you have to compute a coefficient, and you can prove actually that this sigma, so I refer to the book of Perko, you can prove that the sigma is -3. And you can do all the computations and it works well, and you prove that you have a supercritical of bifurcation. I will give the proof of the general result. That is every solution which is not 0, 0 converge to the limit cycle. I will do it quickly on the board. Oh.
Monsieur, j'ai pas très
Oui.
bien la question.
No, je vais, what I'm going to do, let me do something. So I just want to quickly, I'm just showing you why every solution is going to go towards the limit cycle. So here you have a new line. So this is v equals minus u to the third plus alpha u for alpha positive. So you can prove that, for example, let's start with an initial condition, which is, let's start here. So if you start here, you can see that the trajectory is going like that, and then is going like that, and you're going here. So you define, it's called the Poincaré map. Okay, but what you can prove because of the equation is that, so let's write the axis here. You can prove that if you start with v, which is large enough, the distance here will be smaller than the distance here. All right. And now you have a symmetry within the system. You have a symmetry within the system. That means what? That means if your solution does that, if you start here, if I take here the same distance here and here, you will end up at the same distance here. So we'll go like that. It's the same. So the value here, you find it on the curve also here, and you go like that, and you're here. But then the trajectory must continue, and so you don't have choice. You have to go that, and you cannot cross because of the uniqueness of the solutions. You cannot cross the blue one. So the blue one and the blue one and the red one cannot cross. So you're stuck. You're stuck here. Okay, and here, so it's the same. You go like that, and then you have no choice Okay, since you cannot cross, you will end up here at the point which is less than this one. And you continue, and so if you start here, and if this distance is smaller than this one, you can prove that the successive points here are decreasing regarding the distance here. And if you start for a small value here, then the real part of the eigenvalues are positive. Actually, this is a source. So if you start close enough of 0, 0, you have any choice. If you start here, after you do that, and you can prove that the distance here will be greater than the distance here, and then you can prove that your sequence here is positive, which means that if it's negative, you have a decreasing function. If it's positive, you have an increasing function, and you only have here one possibility is that when you apply this thing, you will get a fixed point, and this is your limited cycle. So it was just the idea, but complete proof can be found in the book of Perkle. So I'm not doing more the Blackboard today, and let's go to the presentation. So all right, so okay, those are two possible exercises. Now, okay, so now you can compute the eigenvalues of the linearized operator. This is a classical thing, and you can prove that. So as you can see, when alpha crosses your lambda k, so lambda k is k to the square times pi to the square, and you can see that when alpha equals lambda k, those values are complex, conjugate complex. All right, and you can see that as lambda k is going to infinity, my mu 2k is going to 0. Okay, so I talked about that in the introduction. This brings some technical difficulties. Okay, so if you take now alpha to be greater than 0 but less than lambda 1, and if you assume that, so this means what? This means that, for example, now if you take the initial conditions to be constant, it will go towards the limit cycle. If you take your initial conditions to be constant in space, you will everywhere in X, you will have this kind of behavior. But what we can prove here is that if you choose this kind of
Okay, where did you lose me? So you hear me? Do you hear me?
Yes, it's okay.
Okay, so did you miss something or?
On vous entend bien, monsieur.
All right, that's perfect. So as I said, now, if alpha is greater than 0, it's finished. I mean, the solutions will not converge to 0. But if you choose those specific initial conditions, then the solution is still going to 0. It's an interesting result, because you find a set of initial conditions which is going to 0. Nevertheless, you also find some solutions which are going away from 0. So I will call that a saddle in infinite dimension. And you can prove that. Well, the proof is inspired by the proof that we did before. No, this is another result. Sorry. Yeah. So that's it. So I repeat, it's an interesting result. The point 0, becomes unstable because some solutions go away from 0. They're going to the limit cycle. So if you take initial conditions that are constant in space, they're going to evolve periodically in time and will be constant in space. So it's equivalent to consider a two-dimensional ODE. But if you take these special initial conditions, as you see, for example, if you take the integral between 0 of 1 of u at time 0, it's 0. And the same for v. Then by symmetry, this will remain true. And then you can prove that if alpha satisfies this, you're going to 0. All right. And then you have a more general result because this is a local stability result, again, for alpha between 0 and lambda 1. If you, there is some balls of radius uk such that if you start in this ball, so mu k is going to be small, then my solution is going to converge to the first projection, okay, on the L2 space. All right, so I went to a little bit fast. So those are research results. You need to dig inside. And so there is this paper on arXiv, which is not perfect. There is I have a better version. I can give it to you, but okay, the ideas are all in this paper, which is on arXiv, and you can get more insights on these results. Yeah, I don't give you more details here. Okay, now I just now going to, because it's almost 2 hours, I'm going just to give you now a flavor of what's going on. So now we move forward with my second equation, which is in fact equation number 3. We can take a two-dimensional version of that. And I already show you these patterns, right? But this is a generalization of what I said. So let's show you these patterns again. So these patterns are solutions of this equation. One, this is from a specific initial condition. So here you can see u, the time is evolving, and you see u of x, y, and the color depends on the value of u. This is, again, the solution of the same equation, but with different initial condition. Okay, I will show you that in a few minutes, but now you can see that for every x, the value is the same, almost the same, but it depends on t. And then again, the same equation, but with other initial conditions. So all those are solutions of this equation, but with different initial conditions. All right. I'm sorry. I don't want. Okay. So this is really a generalization of my proposition. I don't remember. Yeah. So you see the proposition of 5. It's in one dimension, and this is really a generalization of proposition 5, but in dimension 2, I can take actually the dimension that I want. And so you can prove that if you have these assumptions, then the integral will remain 0, and which means that you cannot converge to a solution which is constant in space. Otherwise, the integral will not be 0. So here, you can somehow characterize a set of initial conditions which are not converging to the solutions constant in space, although the solutions constant in space attract a lot of initial conditions. This is a numerical result, but yeah, it will be interesting to give insights with some theoretical results on that. Okay, and then, so here I show you 3 things. So this corresponds to the first pattern, the spiral. This corresponds to the second pattern, which are constant solutions in space, and this corresponds to the third pattern. So here I picked up 2 points in the space, and I'm showing you u of this. So in red it's for 1 point in the space, 1 fixed point in the space, and the green one it's for another point. And I'm showing you the time series. Okay, they are not the same, as you see. And as you can see, in blue, it's the integral over all the x. And you see that's 0. Then, in the second picture, you can see that everything is the same, almost. you have a synchrony in the world space. So typically this is an ODE. You don't have space anymore. And however, I started with an initial condition which was not simple, but at the end of the day, for large T, for all point in X, I have the same solution. And this again, this is a specific initial condition with some stochasticity, but with a measure that is not chosen arbitrarily. And you saw the pattern here, and you saw the time series for different X, and this is the mean over all X's. All right. Okay, now what's the difference between equation 3 and 4 is that now I have a dependence on X. You see? So if I consider the equation without the Laplacian here, depending on C, I have two possibilities. At left, you have a unique stationary point, which is attractive. It is stable. And if I start with an initial condition here, I'm ending up on the stationary point. However, if I started here, I will go like that, then like that, then like that, and then like that. It's called an excitable system.
C is a vitesse?
No, C is just a parameter. It appears here. So this is the solution for C equals minus 1.5. This has nothing to do with traveling waves. Well, it could, but this C has nothing to do with the speed of a traveling wave. It's just a parameter. It do have a relation with the excitability of the system. It's kind of a neuron. If you stimulate here, it has a threshold. If you go beyond the threshold, you get a spike, an action potential. But if you do not go beyond the threshold, you don't have a spike. All right, but if you take C equals 0, you have a limit cycle. For C equals 0, it's a special case of the toy model. For C equals 0, we have already considered this equation. All right. So now I will make C depend on X. So if I generate oscillatory signal, thus my PDE will propagate these oscillations. So what I am considering for X in the center of the domain, I choose 0, and for X not at the center of the domain, I choose a value C0 which is less than 1, so that it corresponds to excitatory dynamics for the ODE. And this is the result. So if my C0 is minus 1.2, I don't move. I got a stationary solution. If it is minus 1.01, it does move. It moves. I have propagation of excitation through my domain. And for a value in between, I have propagation, but as you can see, you have at the center, you have small oscillation, then large oscillation, small oscillation, then large oscillations. And this is again for, now this is for a fixed x, which is at the center of the domain. It's, for example, x equals 0. This is called mixed mode oscillations. All right. So now we can prove some results. So again, if you consider the PDE, you will have some results. So here, this theoretical result is for dimension 1. So it's like it's the same approach than in the toy model, but of course, for proving that you go through a cascade of bifurcations, it's not so easy. But you can prove that you have an Hopf bifurcation. And you have this local stability result. But things are more complicated because here you have a dependence on x. And this is the same thing with things in a two-dimensional setting. And this is just, I already showed you, but this is to if you choose a C of x to be more complicated, you can have more complicated patterns here. So you have these irregularities in the domain, which makes the signal hard to go through. All right, so then it's just to make the link what we have done at the previous lecture. So of course now you can consider networks of these equations and you can get the proof. I already discussed that last time. And that's it. So if you want to work on that, you can choose whatever you want and work on, and come to see me with some interesting results and work. And I will be happy to listen to you and to give you a grade on that. Okay, so see you next week, and that's it.